Thank you very much. Greetings to everyone. First of all, I would like to thank very much the organizers to offer us this possibility. Of course, we all know that the best way to have a mass conference is to meet together in some place like Marseille. The second best thing is when this is not possible to have a virtual conference. So thank you very much for making the effort for this. So the plan of the talk is, after a short introduction, I will say a few words about the Biluti theorem, and then I will address three topics in which, with some co-authors, I have a few results concerning Diophantine equation in separated variables. Not all of them are connected to the Biluti theorem. There are also some results which will be effective results. So first of all, if we take the Diophantine equation of the shape fxy equals 0, where fxy is a polynomial with rational coefficients, then in principle the main question may be how this, or when this equation may have finitely or infinitely many solutions. And of course, we know that if fxy is irreducible over Q, but it is not absolutely irreducible, so it's not irreducible, let's say, over C, then fxy equals 0 has finitely many rational solutions. Denoting by G the genus and by D the number of points at infinity of the plane curve fxy equals 0, in 1929, Siegel answered this question quite completely. In principle, his result says that if fxy is absolutely irreducible and G is larger or equal to 1 or D is larger or equal to 3, then one has only finitely many solutions. So Siegel's result is very helpful when the polynomials are given explicitly or when they are of a very special form. But in principle, it was for a long time a question whether we can describe all the pairs of polynomials f and g for which fx equals gy, which is a special case of the previously shown equation. The case when the variables are separated, x is in the left-hand side, y is on the right-hand side. Can we describe all the situations when this may have infinitely many solutions? In the type of equations with separated variables enter many important special cases, many important classes of Diophantine equations, like superelliptic equations, hyperelliptic equations, Schinzel-Tiedemann equation, power values in arithmetic progressions, or power values of the sum of case powers, equal values of Lacunary polynomials, and several other classical and important Diophantine questions. Now, the question of describing all pairs of polynomials such that the equation fx equals gy has infinitely many solutions has been solved by Bilo and Pihi. In principle, this is a widely known and appreciated theorem, which became a very important tool in Diophantine number theory. They proved that if f and g are polynomials with rational coefficients, which are non-constant, then the following two statements are equivalent. Equation 2 has infinitely many solutions in rational numbers with bounded denominator. In principle, it's a kind of generalization of the searching for integer solutions. So this statement is equivalent to the fact that f is composed of three functions, three polynomials, and g is composed again of three polynomials, where the inner polynomials are linear polynomials. The middle polynomials form a so-called standard pair, which on the next slide I will show how they look like. And phi is just a polynomial with rational coefficients, and it also has to be assumed that the equation fx equals gy does have infinitely many solutions in rationals with bounded denominator. So in principle, this is a very concise description of all the cases in which it is possible that this equation does have infinitely many solutions. And there are the possible pairs for G and F, or F and G, of course. Interchanging the order doesn't make any difference. So there are 5 types of polynomials. The first type of polynomials look like x to the power q and this product afterwards. The second type is x squared and alpha x squared plus beta times vx squared, where here alpha beta are non-zero rational numbers, and the third types of and fourth type of pairs are defined using the Dixon polynomials. And finally, there is the fifth pair, where there are not many restrictions on the parameters. So these are the possibilities. Since this is a very concise and precise description of all the situations, and there might be infinitely many solutions, the Biluty theorem became a widely used tool for proving finiteness of number of solutions in the case of Diophantine equations. I cannot list all or nearly all or not even all the important results where the Biluty theorem has been used, but I just show a few instances of the use of them, maybe some of which I knew without searching for them. So Peter, Pinter, and Schinzel, and later Schinzel alone, applied Biluty theorem for separable equations in trinomials. Stollentihi investigated the problem for general Meixner and Kravchuk polynomials. Bilu, Brinzok, Inscherhofer, Pinter, and Tihi used it for Bernoulli polynomials. Kreshow for lacunary polynomials, Dubiskat and Kreshow for truncated binomial powers, Rakowski for polynomial values of power sums, and Kulkarni and Sari for polynomial values of products of consecutive numbers. So to start to present some results, first of all, let us define the sum of products of consecutive integers. In principle, this is a polynomial which is defined by the sum of the product of terms like x plus j. So if we start to look at the first such polynomial, f0 of x, that's nothing else, just x. f1 of x is x plus x times x plus 1. f2 of x will be x plus x times x plus 1 plus x times x plus 1 times x plus 2, and so on. So in principle, what is clear from the definition is nothing else that f of x is a monic polynomial, clearly. Then it has positive integer coefficients. Its degree is k plus 1. And well, as we see, it is also visible from this that 0 and minus 2 will be always the root of this polynomial. These polynomials first were introduced, as far as I know, by Hajdú, Lajström, and Tengely, who proved that the Diophantine, who considered the Diophantine equation fk of x equals y to the n, and they proved effective finiteness result for that. They even solved completely the equation when 1 smaller or equal to k smaller or equal to n. And to do so, they needed a few more involved properties of these polynomials. So about the fk of x, here are the first few polynomials. And if k is larger or equal to 3, then all the roots of the polynomial fk of x are real and simple. So the only case when there is a double root is here in f2 of x. 0 is always a root and -2 is always a root of the polynomial. And a more precise description of the root structure of fk of x is here. These are the intervals where fk of x does have a root. So in principle, each root can be put in an interval of at length at most, well, 1.5, but generally 1. So it is very well described where are the roots of this polynomial. Okay, so for our generalization of the result of Hojdula and Tengely, we needed some properties of the polynomials fk of x plus 1 and fk derivative of x. Sorry, from here the k is missing. So if k is larger or equal to 3, then all the roots of fk of x plus 1 are real and simple. That's one property which we will use later. -1 is always a root of the polynomial fk of x plus 1 for all k larger or equal to 2. Again, for k larger or equal to 2, we can describe where the roots of this polynomial fk x plus 1 reside. One of them is in the interval -k minus 1 minus k, the next one in -k minus k plus 1, and so on, up to -3 minus 2, and finally there is one root in the interval -0.50. So for k larger or equal to 3, if we consider the derivative of such a polynomial, then we can denote the roots by alpha 1, alpha 2, and so on. All these roots are real and simple, so it will have exactly k roots. If k is larger or equal to 6, then we can prove that fk derivative in 0 is positive, fk derivative in the value -1 gives a negative value, and so on. And for k larger or equal to 13, we just have fk alpha 1 is larger than fk alpha 3 is larger than fk of alpha 5, and fk of alpha 2 is larger than fk of alpha 4. These are properties which we needed in the proofs of our results. Among the first results, I will mention that fk of x is indecomposable. So let us see what we mean by a polynomial being indecomposable. By a decomposition of a polynomial f of x over a field k, we mean that it is written as a composite function of two polynomial functions. So it is of the form g1 of g2 of x, where g1 and g2 are both polynomials over the same field. And we say that such a decomposition is non-trivial if the degree of both these polynomials g1 and g2 is larger than 1. So if none of the polynomials g1 and g2 is linear. If we have two decompositions, we say that these decompositions are equivalent if there exists a linear polynomial with coefficients in the field k such that g1 can be expressed by h1 in the variable lx, and h2 of x is L of g2 of x. We will say that the polynomial f of x is decomposable over k if it has at least one non-trivial decomposition. Otherwise, it is called indecomposable. And what we proved together with Vasó, Hajdú, and Luca was that the polynomial fk of x is indecomposable over the complex field for any k larger or equal to 0. To prove this, we had two very nice tools. two lemmas of Dujela and Gusic, they proved that if fx is a polynomial with integer coefficients, which is monic, and it is decomposable over the complex field, then there exists also decomposition over Z. Further, they also proved that if we have a polynomial f of x, which is monic and has integer coefficients, then in the case of any decomposition, f of x equals gh of x, the outer polynomial, the degree of the outer polynomial is such that its degree is smaller or equal to the GCD of the second coefficient and the degree of the polynomial. So whenever we have a decomposition, the outer polynomial is of degree less than the GCD of this coefficient and n, the degree of the polynomial. This means that the GCD of a and n, if this is co-prime, then m is smaller or equal to 1. That means that if a and n are co-prime, then any decomposition is with degree of g equals 1, which means that f is indecomposable. So any decomposition would be a trivial decomposition. So let us see how can we use this for proving that fk of x is indecomposable. First of all, let us see how fk of x looks like. We know that fk of x has degree k plus 1. It is monic. So we just denote its coefficient by 1 ck minus 1, and so on, c1. And we know that 0 is a root of fk of x, so c0 must be 0. It is not very hard. I would say it is very easy to compute ck, which is 1 plus k times k plus 1 over 2. Now, if we take a look at it, this, when k is even, then this is k plus 1 times an integer. If I add 1, that is co-prime to k plus 1. So in this case, by the theorem of Dujela and Gusic, fk of x is indecomposable. This is the easy case. When k is odd, then we have to do a little bit more of computations. In this case, we see that k plus 1 and ck has a GCD which is at most 2. Well, of course, in the case when the degree of the outer polynomial, if fk of x equals h of g of x, if the degree of the outer polynomial is 1, that's a trivial decomposition, so it doesn't count. So the only way we may have a non-trivial decomposition is that degree of h is 2, because the degree of the outer polynomial, of the external polynomial, must be smaller or equal to 2. So assume that we have a quadratic polynomial, h equals ax squared plus bx plus c. Now then, h of g of x looks like this. And clearly now, this is a decomposition of the polynomial fk of x. But by the theorem of Dujela and Gusic, we know that if it has a decomposition over the complex numbers, it has a decomposition over the integers. So we may assume, without loss of generality, that a, b, c are integers, and g is a polynomial with integer coefficients. From this, it is easy to see that a must be equal to 1, because f has leading coefficient 1. So this means that a times the square of the leading coefficient of g must be 1. All are integers, so a must be 1. This means that if u and v are the polynomial are the roots of the polynomial h, the quadratic polynomial ax squared, or now x squared plus bx plus c, then fk of x can be written like g of x minus u times g of x minus v. But we know that fk of 0 is 0. So either one or the other factor must be 0. So we get G0 equals U or G0 equals V, which now shows that either U or V is integer. But now we have a quadratic equation. If one of the roots is integer, then the other one must be integer. So both U and V are integers. So we may just denote Gx minus U by H. And then we know that Gx minus V will be H of x plus D, where D is U minus V. But what is important, that this D is an integer. So now we have Fk of x equals H times H plus D. And let us use the property of Fk of x, that Fk of minus 1 is minus 1. That means that H of minus 1 times H of minus 1 plus D, they give minus 1. So since H of x and H of x plus D are integers, then H of minus 1 equals plus or minus 1, and H of minus 1 plus D equals plus or minus 1. Consequently, we obtain D equals 0 or D equals plus or minus 2. But D equals 0 would mean that Fk of x is H of x to D squared. But this contradicts that all the roots of Fk of x are simple roots. And when we have D equals plus or minus 2, then we get that Fk of x plus 1 will be a square. But again, we have proved that Fk of x plus 1 has only simple roots, which gives again a contradiction. So altogether, Fk of x is indecomposable. This theorem was used to prove the second part of the following more general result. Let g of x be a polynomial with rational coefficients, and consider the Diophantine equation Fk of x equals g of y. So now the right-hand side is an arbitrary polynomial, and on the left-hand side we do have this polynomial, which is the sum of products of consecutive integers. Assume that k is larger or equal to 3. Then in the case when the degree of the polynomial g is 0 or 2, then there exists an effectively computable constant depending only on this index k and the polynomial g, such that the maximum absolute value of the integer solutions of equation 4 is bounded by this constant. So we can prove an effective finiteness theorem in this case. Whenever the degree of g is larger or equal to 3, then we can prove that equation 4 has only finitely many integer solution, unless we have g of x equals fk h of x. Clearly, in this case, there will be infinitely many solutions. So, in the case of g equals 0 or 2, we have effective finiteness, and in the case of g larger or equal to 3, we do have ineffective finiteness. Here in the second point, the finiteness is ineffective because we are using the Biluty criterion, the Biluty theorem. And since the Biluty theorem is ineffective, the results proved by it will also be an effective result. This means that there are no bounds on the size of the solutions. It proves a finiteness where there is no guarantee that there is a bound. We cannot just produce an effective upper bound. What about the cases which are excluded? First of all, whenever g of x equals fk of h of x, then clearly we may have infinitely many solutions. Also, when degree of g equals 1, we may have infinitely many solutions. Well, it is clear whenever g is linear, then this might have infinitely many solutions. let's say if g of I equals y, then we just have fk of x equals an integer, and if y is that integer, that's a solution. So for every x, we get a solution y. Again, when g of x is fk of h of x, the same situation holds. Whenever h of x assumes a value, then we can take for, let's say for y, or for the other unknown, this value, and we get a solution. So in these cases, we always have infinitely many solutions, and it may happen also for k smaller or equal to 2. At the beginning of the theorem, we assume k is larger or equal to 3. Well, when k is smaller or equal to 2, it may happen that there are infinitely many solutions. These conditions are necessary now in case of our theorem. Now, a few words about the proof of statement 2. I will not tell anything about the proof of the first statement, but about the second statement, where we use the Biluti theorem, I would like to sketch the main ideas of the proof. So it is this part of the theorem. So, as in the theorem, we assume that k is larger or equal to 3, and the g is a polynomial with rational coefficients of degree at least 3. And we assume that this equation has infinitely many solutions. Now let us see what can we infer from that. The Biluti theorem describes very explicitly in what situation this can happen. Fk of x must be phi of f of lambda of x, and g must be phi of g of k of x. The phi here is the same polynomial. Lambda and kappa, they are linear polynomials. And f and g are coming from a standard pair over q. Now, we have proved a few slides before that fk of x is indecomposable. So that means that the degree of this phi is either 1 or it is k plus 1. If it's 1, then of course f must be of degree k plus 1, otherwise f will be linear. So let us see the two cases. We will address first the case when degree of phi of x equals k plus 1. We just recall that this is how fk and g of x are composed. Now, from this composition, we see that the degree of f must be 1, because this is of degree k plus 1, phi is of degree k plus 1, so f must be linear. But then, clearly, we have fk of x equals phi t of x, where t of x is f lambda of x. It's linear. Now we can take the inverse function of the polynomial function t of x, so that t of t minus 1 gives the identity function. So this means that fk of t minus x is just phi of x. So we can express phi of x in the form fk of something which is linear. Now, if we go to the other part of the other polynomial g of x is composed like phi of g of kappa of x, but phi can be written like fk of t minus 1. And now you see that this is fk of something. And in principle, we don't care what is here inside. The only important feature is that it is a polynomial with rational coefficients and of degree at least 1. So this means that we can prove that g of x equals fk of h of x. This is the exceptional case when we may have infinitely many solutions. And we will see that there are no other possibilities for infinitely many solutions, since the other possibility is when the degree of phi of x equals 1. Whenever the degree of phi of x equals 1, we can write phi of x like this. And in this case, we have to study all the possible standard pairs. Now, we have 5 kinds of standard pairs. In the case of standard pairs of type 2, this can be excluded because there we have a polynomial of degree 2. But f of x and g of x cannot be of degree 2 in this case, because f of x must be of degree k plus 1. If I go back here, now phi is linear, lambda is linear. So in order to get a polynomial of degree k plus 1, f must be of degree k plus 1. It cannot be a quadratic polynomial. So on the other hand, the other polynomial, let me just come back for a second here to the second type standard pairs. So one of them must be x squared, and the other one must be of this shape. But here it's clear that this polynomial has multiple roots whenever the degree is larger than 2, or larger or equal to 4. Sorry. So in that case, again, we see that it has multiple roots. But fk of x cannot have multiple roots. So this way we can exclude polynomials of pairs of polynomials of type 2, standard pairs of type 2. Standard pairs of third and fourth kind, they are the polynomials which are defined using Dixon polynomials. We can exclude them by comparing coefficients in this equation. In the case of standard pairs of type 5, in principle, we have 2 cases. Fk of x must be either of this shape, which contradicts with the indecomposability of f. If we look at this, then this shows that there is a polynomial a times lambda x squared minus 1 to the cube. But this means that this polynomial is composed to phi x cubed plus phi 1 x cubed plus phi 0. So this is a non-trivial composition of polynomials. Fk cannot be of this shape. On the other hand, we may have fk of x equals this shape. And in this case, we just compare again coefficients, and after comparing 3 for coefficients, we get a contradiction. In the case of the first type, again, the root structure of fk of x and the derivative of fk of x prove that such standard pairs are impossible. Well, of course, here we have some lengthier computation, which I have no time to show for these situations, but this is the flavor of the proof. We also proved an effective result. In the case of the equation fk of x equals ay to the n plus b, we could prove that the solutions are bounded by an effectively computable constant. Well, this is a generalization of the result of Hoydul, Leishram, and Tengay, who considered the case a equals 1 and b equals 0. Now we will switch our attention to a different topic. Komornik polynomials are polynomials introduced by Vilmos Komornik for some results concerning digital expansions. If we define a sub n of x equals x to the power 2 times 3 to the power n minus x to the power 3 to the n minus 1, and we multiply such polynomials from k equals 0 to n, then we get the nth Komornik polynomial. Komornik polynomials, the first few of them look like this. The first one is easy to see, but the second one and the third one are these polynomials. So we can see that these are polynomials with coefficients plus or minus 1, and there are the degree of such polynomials is always 3 to the power n plus 1 minus 1. All coefficients are plus or minus 1. Below the highest degree term, below the main term, there are no other coefficients than plus or minus 1, including 0. There is no 0 coefficient, so all the terms are present. It consists of 3 to the power n plus 1 monomials, and all these monomials have coefficients either plus 1 or minus 1. It is also proved that all the complex roots of such polynomials are simple. The first important result concerning cohomorphic polynomials is that cohomorphic polynomials are incomposable over C. And this helps us to use this to apply the Bérczes theorem later. But for the moment, let us see a few more properties of A k of x. In principle, there is a polynomial identity AL plus k of x equals A sub L of x to the power 3 to the power k. And if we denote the Fibonacci numbers by phi 0, phi 1, and so on, and we define R sub k to be phi of 3 to the power k plus 1 plus phi of 3 to the k minus 1 minus 1, then these are clearly integer numbers. These integer numbers will play an important role in the GCD of two values of this polynomial ak of x. So if we take the polynomial ak of x in any integer base, and we compute it for the index L and for the index L plus k, then the GCD of these two integers will divide the integer R sub k defined just here using the Fibonacci numbers. So this way, for polynomials with index close to each other, we can compute the GCD, or we can prove how much is the GCD. If they are consecutive indices k and k plus 1, then the GCD will always be 1. And if between the indices, the difference is 2, then the GCD is either 1 or 5. So after these auxiliary properties, let us show the results concerning Diophantine equations containing cohomorphic polynomials. The problem originates from Attila Bérczes, who asked in a conference about the finiteness of number of solution of P sub n of x equals P sub n m of y. With Kolusz, Pink, and Szustek, we did prove that the equation P sub n of x equals P sub m of y has always finitely many integer solutions. And even more general, we consider the equation with arbitrary right-hand side. And we did prove that if g of x is not of the form P sub n of h of x, or g of x is not of the form gamma of delta x to the L, where gamma and delta are linear polynomials with rational coefficients, and L is just the degree of this polynomial g, then we have only finitely many solutions. However, I have to mention that the first exception that's necessary. The second exception, we couldn't prove that in this case there are infinitely many solutions, so it probably may be excluded, but we were just unable to prove that. Well, that was what it was written here, and of course, since we use Bérczes theorem, the result is ineffective. We also did prove some results concerning this polynomial which are effective. In the case of the equation P of n of x equals y to the m, we did get effective solutions both in the case m equals 2 or m larger or equal to 3, and we even could prove an effective result for the exponent m from here whenever y is different of plus or minus 1. And for the concrete cases of y square in the right-hand side, we did solve completely this equation. There are some trivial solutions, and except of the trivial solutions, it exists only one non-trivial solution in the case when n equals 2, and we did solve the equation also for n equals 1, 2, 3, 4, and 5. Further, we did prove, we did solve completely the equation P of n of x equals y cubed for n equals 0, 1, 2, and 3. As my time is going, I will not tell about these results in details. However, I will switch to my third topic, power values of power sums. Well, if we take sk of x, 1 to the k plus 2 to the k plus x to the k, this is sk of x, and the problem sk of x equals y to the n. This is a well-known and much investigated classical problem. It goes back to Luca Watson, and the first internationally known breakthrough was due to Scheffer, who did prove that if k and n is not one of these pairs, then this equation 16 has only finitely many solutions. He also conjectured that if k and n are not, kn is not of this pair, not one of these pairs, then the only non-trivial solution is given by 2, 2, 24, and 70. Many results concerning this equation have been established during the last few decades. Yuri, Tiedemann, and Voorhoef proved an effective version of Scheffer, and they have another extra feature that also n was an unknown. So in this equation, also the exponent was an unknown for them, and the effective finiteness was working also in this more general case. Then Pinter proved that for non-trivial solutions we have this bound. The conjecture was verified by Jacobson, Pinter, and Walsh for some bounded values of k and n equals 2. Bennett-Yuri and Pinter extended the result to 1 smaller or equal to k smaller or equal to 11 and arbitrary n larger or equal to 2. This was again an important breakthrough. And Pinter verified the conjecture for n larger than 4 and 1 smaller or equal to k smaller than 107. This is, of course, not a complete list of results. However, Hoydu initiated the investigation of this equation for fixed values of x. For values of x which are smaller than 25 and are congruent of 0 and 3 mod 4, he computed all the solutions, and together with Hoydu, Miyazaki, and Pink, we extended this result for the cases when k is congruent to 1 or 2 mod 4. In principle, this shows that we proved the Scheffer conjecture for x smaller than 25 and n larger or equal to 3. Now, finally, I would like to mention few other kinds of equations where sk of x is included and the Bilu-Tichy theorem is used, but these results are not mine. I couldn't contribute to this topic. Bilu, Brinzo, Kirchenhofer, Pinter, and Tichy, they considered the equation sk of x equals Sm of y, and for the case when g of y is the product of consecutive integers, Bilu, Brinza, Kirchenhofer, Pinter, and Tichy proved again then Gyuri-Kovács, Péter, and Pintér for binomial coefficients, and for this kind of sums, Gyuri-Kovács, Péter, and Pintér. So also for such kind of separable equations, the Biduti theorem was used, and it was a powerful tool. Thank you very much for your attention. This was what I wanted to tell.
Yeah, so thank you very much, Attila, for your very nice and rich talk. So it's open for discussion, and I already can see a very precise question by Gary Walsh, who is our next speaker. So the question you can read here, is it possible to read it?
Just a second, I'm trying to...
So he is asking, where do the upper bounds come on page 28?
On page
very precise question.
Page 28, just let me find... Oh, no, it's 30 now? No, it's 20, oh. It's
yeah, 28.
Oh, I see. These are coming from super and hyperelliptic equations from Baker's theory, from a result of Jan-Henrik Evertsche, Kálmán Győri, and myself. We have a completely explicit result for this case, and we use that theorem for this.